Okay, in this video I want to talk about the next step in the modernization of astronomy that happens during the time of what we would call the scientific revolution, the late part of the 16th century, early part of the 17th century. In a previous video we talked about Copernicus and Galileo. Now I want to talk about the next generation of scientists, Johannes Kepler and Isaac Newton. Kepler was actually a contemporary of Galileo. They overlapped, but Kepler had a somewhat different focus than Galileo. While Galileo was interested in observing the sky with his telescope to see what's really going on with Jupiter and the sun and the moon and so on, Johannes Kepler was focused on predicting the motions of the planets in the sky. And to do so, he took a bunch of data that had been collected from other people, most notably Tycho Brahe, who I would love to do a lecture about Tycho Brahe, but we just don't have time. And rather than take the approach that, say, Ptolemy took, which was, what kinds of circles can I put in the sky in order to make the planets do what they do? Kepler took the approach of, let's just actually plot the path that the planets take through space and figure out what that path is and see if we can describe that using mathematics and the tool set of astronomy at the time in the early 1600s. Johannes Kepler published three important works in the history of science: Astronomia Novia, New Astronomy, Mysterium Cosmographicum, and Harmonice Mundi. The second two are really peculiar works that we don't consider scientific nowadays. On the Harmony of Worlds, tried to explain the speeds of the planets around the sun in terms of the frequency of notes in a musical scale. So literally the Harmony of Worlds was suggesting that the design of the solar system in terms of the timing of the notes was the same as the design of a musical scale. Not true, and not today an idea that we would consider scientific. Mysterium Cosmographicum, which an image from Mysterium Cosmographicum makes up the background of the first part of my presentation here. The idea behind Mysterium Cosmographicum was to try to explain why there were, how many planets? Mercury, Venus, Earth, Mars, Jupiter, Saturn, 6 planets. And the way Kepler tried to explain that was by imagining that the spaces between the planetary orbits corresponded to certain mathematical shapes. There are 5 mathematical shapes that are called perfect Platonic solids. The tetrahedron, the 4-sided pyramid, the cube, the octahedron. If you play Dungeons and Dragons or any role-playing games, you'll recognize these as the 4-sided, 6-sided, 8-sided, 12-sided, and 20-sided dice. 5 shapes that are perfect polygons. Every side is the same shape with the same length and the same angle. There's only 5 ways to do that: the tetrahedron, the cube, the octahedron, the dodecahedron, the 12-sided with 12 pentagons, and icosahedron. And Kepler tried to put these shapes inside of one another. A tetrahedron inside of a cube, inside of an octahedron, inside of a dodecahedron, and to see if those distances corresponded to the sizes of the orbits of Mercury, Venus, Earth, Mars. They don't. It's a crazy idea. It's an idea that we wouldn't consider scientific today, largely because we know today that there are not just 6 planets. There are 8 planets or 9 planets or 30 or 40 planets, depending on what you want to call a planet. So not all of Kepler's ideas were what we would consider today properly scientific ideas. They were kind of a weird combination of numerology and pure mathematics. But Astronomia Novia, New Astronomy, was science. It was based on the Copernican idea that the Earth and planets go around the sun. Kepler had no doubt about this model of the solar system. We know that Johannes Kepler owned Copernicus's On the Revolutions of the Heavenly Spheres. We know this because we have his copy of it with his notes in it. So Kepler was a Copernican. He was a heliocentrist. He believed the planets went around the sun, and he took the data of Tycho Brahe and tried to actually plot in space the path that the planets travel. And in the process, he discovered 3 facts about planetary motions that we today call Kepler's laws of motion. The first fact is this: planets do not move in circles or circles on circles, or circles on circles on circles around the sun. The shape that a planet moves around the sun is an ellipse, a specific kind of mathematical oval that if you took an analytic geometry class in high school, you might know all about ellipses and their properties. Suffice it to say, a circle is an ellipse, but it's a round ellipse, just like a square is a rectangle, but it's a rectangle where all four sides are the same. Now, this ellipse I've drawn here is greatly exaggerated for the planets in our solar system: Mercury, Venus, Earth, Mars. The orbits of the planets are very close to circles. The eccentricity or the ovalness of the ellipse is very small for the planets in our solar system. It's big for asteroids and comets, but it's small for planets. So we didn't notice for hundreds of years that planets don't move in circular paths at all. They move in elliptical paths. And the sun is located at one focal point of that ellipse. If you want to know how to draw an ellipse, the way you draw a circle is you pin down a piece of string and you put a pencil at the end of that piece of the string and you draw a shape that's always the same length from the center. The way you draw an ellipse is you put down two pins and you connect a piece of string to both pins and you put your pen in that circle so that the total length of the distance from one focus to the ellipse to the other focus is always the same. That's the mathematical shape called the ellipse. So Kepler's first law just tells us that planets move in an elliptical path with the sun at one focal point of the ellipse. The second law says that planets do not always move at the same speed, the way Aristotle and Ptolemy assumed that they must. Planets speed up and slow down. When they're going close to the sun, they move faster. When they are further from the sun, they move slower. And they speed up and they slow down in a particular mathematical way that Kepler was able to figure out. The way they speed up and slow down is they speed up when they're close to the sun and they slow down when they're far from the sun in such a way that this arc, this slice of this pie here, if this is the same time from here to here and from there to there, that slice is always the same area. So if we look at the motion of the planet in 1 hour, let's say, the area swept out by this line connecting the planet to the sun is always the same area when it's close to the sun and far from the sun. Or if this is how far it moves in a day, that area swept out by that line is always the same whether it's close to the sun or far from the sun. So this is a mathematical relationship that tells you how much a planet speeds up and slows down. It depends on how much its distance changes from the sun. The third law that Kepler discovered was a relationship between how fast the planets go around the sun and how far they are from the sun. We had known for hundreds of years that Mercury and Venus go around fast and Jupiter and Saturn go around slow. But Kepler determined a specific mathematical relationship between the size of the orbit, what he would call what we would call for an ellipse, the semi-major axis, sort of the longest radius of the ellipse, and the period, the amount of time it takes it to go around. And it's a very peculiar mathematical relationship. It says that the square of the period is proportional to the cube of the semi-major axis. But if you take every planet in the solar system, this would be a good homework activity. Look up the periods of Mercury, Venus, Earth, and Mars. Look up the semi-major axis of Mercury, Venus, Earth, and Mars. Square the period, divide by the semi-major axis, and find out if this is always the same number. It is. That's what Kepler discovered, that there's a relationship, a mathematical relationship that all the planets obey. We call these three laws together Kepler's laws of planetary motion. Planets move in elliptical orbits with the sun at one focus. Planets speed up and slow down in such a way that they sweep out equal areas in equal times. And the square of the period of the planet's orbit is proportional to the cube of the radius of the orbit of the semi-major axis, the longest radius of the elliptical orbit. One thing that it's important to recognize about Kepler's laws is that they are empirical. That means that they are based entirely on observations. There is no explanation to be found in Astronomy and Novia or anything Kepler wrote as to why this is true. Why do planets move in elliptical orbits? Why do they speed up and slow down? Why is the square of the period proportional to the cube of the size of the orbit? That's not what kind of discovery Kepler made. Kepler did not make a why type of discovery. Kepler made a what type of discovery, or a how type of discovery. How do the planets move? It's important, but it's not an explanation. In a separate video, I have a discussion about the different kinds of explanations that we have in science. What is the difference between, say, a fact and a law and a theory? And we'll use this as an example when we have that discussion. The why to Kepler's laws would have to wait until the next generation of scientists, and that would be Isaac Newton. Isaac Newton lived from 1642 to 1727, so about a generation after Galileo. His three most important works were Optics, where he explained how prisms work and refraction, and that white light is made up of a rainbow of different colors. That's all Isaac Newton. The Method of Fluxions, where he described a mathematical toolbox that today we would call calculus. Newton is credited as the inventor, at least the co-inventor of calculus as a mathematical set of methods. And Principia Mathematica, which we will talk about most in this course, and which I talk about in my physics course, where Newton essentially discovered the laws of motion that were a replacement for the old, bad, wrong physics of Aristotle that we talked about when we talked about Galileo. This is the title page of Newton's book, Philosophia Naturalis Principia Mathematica, which in English translates to philosophy, natural, principles, mathematic, or if you change the word order to correspond to the way we order our words in English instead of Latin, mathematical principles of natural philosophy. I said when we talked about Galileo that these guys in the 1600s would not have referred to themselves as scientists. They would have referred to themselves as natural philosophers. They are people who study the philosophy of nature. And Newton is setting down certain mathematical principles as a way of describing nature that was new and different from anything that anyone had done before. So the mathematical principles of natural philosophy we usually abbreviate as just Principia Mathematica, or most often just the Principia, or Principia or Principia, depending on how you think Latin C's are supposed to be pronounced. I will usually say Principia. Sometimes I'll say Principia. Probably the most important work in the history of science, and I'm not just saying that because I'm a physicist. Newton's Principia established not just a bunch of facts about physics, but a methodology for how science is supposed to be done. That is really the methodology that we still consider science today. The part of Newton's Principia that you're probably familiar with, whether you know it or not, is his laws of motion, legis motus, law, like legal, legis motus, motion. His laws of motion, like an object at rest remains at rest unless acted on by an outside force, and an object in motion remains in motion in a straight line unless acted on by an outside force. That's his first law of motion. Second law of motion, force equals mass times acceleration. Third law of motion, every action has an equal and opposite reaction. People probably have heard of these things even if you don't 100% know what they mean. If you don't 100% know what they mean, you can take my physics class instead of this astronomy class. But these explanations for how and why things move serve as a replacement for Aristotle's notions of how and why things move. Remember, Aristotle said the reason a rock falls when you drop it is because it wants to move down to the earth. Newton says, no, nothing wants to move any particular way. The only thing things want to do is to keep doing what they are doing. If the rock moves towards the earth, it is because some force is making it move towards the earth. That's Newton's second law. So the replacement of natural motions and natural substances with forces that cause motions is a new way of thinking about how and why things move that very quickly becomes the dominant way of thinking about motion. Most of the Principia is really complicated geometry and calculus that if you took calculus today and then opened the Principia, you wouldn't recognize what Newton is doing as calculus. He's doing it in a way that's geometrical, in a way that doesn't use the same modern vocabulary that we use. But if you look at it very closely and figure out what he's doing, eventually you realize, oh yeah, that's just a kind of really complicated geometrical version of calculus. I would guess that there aren't 100 people alive today who could follow all of the proofs in the Principia. It's a different mathematical toolbox than we use today. One of the most important things that Newton realized, first of all, was that in order for something to go in a circle, like the Earth around the Sun, or the Moon around the Earth, or Jupiter's moons around Jupiter, there has to be some kind of force pulling towards the center. If I've got a ball, the way I make it move in a circle is to tie a string to it and hold the string and give it a whirl, and it's the string pulling towards the center that makes the ball move in a circle. Nothing moves in a circle by itself. Moving in a circle requires a pull towards the center, what we call a centripetal force. The other thing Newton realized is that an orbit, like the sun around the Earth around the Sun, or the Moon around the Earth, or Jupiter's moons around Jupiter, an orbit is a kind of free fall. Newton imagined shooting a cannonball off a high mountaintop, and it would go a certain distance. And if you shoot it faster, it would go further. And if you shot it really fast, it would go halfway around the Earth. And if you shot it fast enough, that cannonball would go all the way around the Earth and come back again, and that's what an orbit is. An orbit is a kind of falling where the speed is too fast for it to ever reach the ground. So Newton's big insight was to recognize that a ball falling towards the ground, like a cannonball shot out of a cannon, and a moon moving around a planet are not that different in terms of the kind of motion. And that what they both require is some kind of attractive force to make that curving path happen. You might often hear that Isaac Newton discovered gravity. And you might think, what does that mean? People knew about gravity, right? People knew that things fall. Sure, people knew that things fall. The why was all wrong. Aristotle's why things fall was nonsense. But what Newton discovered is that gravity is an attractive force, and that it's the same attractive force that causes a rock to fall towards the Earth, and the moon to orbit the Earth, and the Earth to orbit the sun, and Jupiter's moons to orbit Jupiter, and Saturn's moon Titan, which had been discovered by now, to orbit Saturn. And that all of these orbiting motions, all of the planets around the sun, all of the moons around the planet, were an expression of the same attractive force. And that's the same attractive force that causes a rock to fall on the Earth when you drop it. That's what we mean when we say that Newton discovered gravity. He discovered that orbiting planets and orbiting moons and falling rocks were all experiencing the same force. Newton not only discovered that this force existed, he came up with an equation, mathematically, to describe how strong that force was. The raw material for his discovery of this equation was Kepler's third law. Kepler's third law is a relationship between how big the orbit of a planet is and how fast it moves. And that's all Newton needed to figure out how strong the force has to be to hold that planet in orbit. Newton's mathematical law looks like this. It says that the force between any two objects in the universe that you might choose is equal to the mass of the one object times the mass of the other object divided by the distance between them squared. And then to get the units right, you multiply by this number called g. G is called Newton's gravitational constant. It is a small, small number. The reason it's a small, small number is because gravity in the universe where we live is a very, very weak force. If you were in a classroom and you wanted to calculate the gravitational force between you and the person sitting next to you, you would take your mass, 70, 80 kilograms, times their mass, 70, 80 kilograms. Divided by the distance between you squared, about a meter. And then you would multiply by this number, and this number is 0.0000000000667. It's a tiny, tiny, tiny number. And the force that you would get is a tiny, tiny, tiny force. Well, of course it's a tiny, tiny force. You don't feel the gravitational attraction of the person sitting next to you in class. You don't feel the gravitational attraction of a truck when you walk past it. Why? Because this number g is very, very small. The only gravitational attractions we feel are the gravitational attractions of very, very large objects, like this big ball of rock that weighs 6 trillion kilograms that we happen to be standing on top of. But there is a gravitational force of attraction between you and the person sitting next to you. And there is a force of attraction between you and the planet Mars right now, and a force of attraction between you and the Andromeda Galaxy right now. And in order to calculate that force, you take your mass times the mass of the other thing, divide by the distance squared, and multiply by 0.000000667. In metric units. In pounds and feet, it would have a different value. This is really important. And it's not just important because it gives us a way to calculate the paths of planets and moons, which it does, and that's super important by itself. But it's also important because it was the first time, too much in the frame right now, it's the first time that anyone suggested that there was a law of physics. I'm going to disappear here for a second. That there was a law of physics, a mathematical law, that could apply to any object in the universe. The reason we call this law Newton's law of universal gravitation is because the two m's in that formula can be any two objects you want. Any two objects with mass exert a gravitational attraction on one another. It was the first attempt by anyone to invent a causal, mechanical, quantitative, predictive law that could be applied to any object in the universe. Okay. That is a major milestone in the history of science. Not just physics, not just astronomy, but science, period. So what did Isaac Newton do? He developed laws of motion that replaced the old bad, wrong physics of Aristotle. He came up with a set of quantitative tools, mathematical laws of motion, that allowed us to actually make mathematical predictions of how things will move and how planets will move through the sky. Not just what did we observe them to do, like Kepler or Ptolemy or the ancient Maya, but why do they move in that way? What is the cause of that motion? And second, more importantly, philosophically, Newton established that there are universal laws that apply in our universe. That there are laws of physics, causal, mechanical, quantitative laws of physics that can be applied anywhere in the universe. It's remarkable, or it would have been remarkable to someone who lived before Newton, that Newton's laws of motion also predicted the motions of Uranus, Neptune, and Pluto that hadn't been discovered yet when he developed those laws of motion. They explain the motion of binary star systems around one another. They explain the orbits of planets around other stars that nobody even imagined existed when Newton came up with these laws. So the power of Newton's laws and the power of physics as an idea is that is universally applicable to everything in the universe. And that is why we credit Newton with the discovery of gravity. He discovered that gravity is something universal that we can apply to any objects in the universe. In an upcoming lab, we'll take a look at just some simulations where we change the speeds of objects and we change their mass, and we see how the shape of an orbit around the sun or around a moon, how it changes as you change the speed of the object. One of the things that makes it hard to do astronomy labs is we can't make two rocks in a lab orbit one another. They're not massive enough. So a lot of the labs that we do in an astronomy class will be simulations. So we'll take a look at a simulated orbital motion using a simulated gravitational attraction that happens entirely inside the computer. And the reason for doing this is to kind of just get a feel for what it takes for an object to move in a perfectly circular orbit or almost perfectly circular orbit the way the planets in the solar system do.